So let's look at ionic bonding and Lewis theory. So let's draw Lewis symbols for potassium and chlorine. Well, potassium is capital K, and how many valence electrons does potassium have? What group is it in? Group 1, 1 valence electron. Chlorine? How many valence electrons does chlorine have? 7. 1, 2, 3, 4, 5, 6, 7. So, according to Lewis theory, here we have a metal and a nonmetal. Metals are willing to give up electrons, nonmetals like to gain electrons. What can these guys do so they both get an octet? Well, potassium can give its electron to chlorine. And when that happens, now potassium has a positive 1 charge and chlorine has a negative 1 charge, and they're very attracted to each other. It doesn't look like potassium has an octet here, though, does it? It looks like he's lost all of his clothes. Well, this is the electron configuration for potassium. There's its 1 valence electron. When we get rid of that, what's underneath? 3s2, 3p6. There's an octet in the previous level. We've just peeled off this partial skin on the onion, and underneath is a full intact layer. So we don't see it in the dots here because we're going to just stay with however many dots we started with is how many dots we're going to end up with. We're not going to be like pulling in these other dots because that would get really confusing. So when an element loses all of its valence electrons, we understand that underneath it has an octet. You can imagine how this negative sign might be kind of get lost in the dots, right? And so typically we're going to put a bracket around all the dots and have that negative charge outside the brackets. So let's use Lewis symbols to predict the formula for the product that forms between magnesium and nitrogen. So how many valence electrons does magnesium have? 2. And then we've got nitrogen. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. So we're going to try to get magnesium and nitrogens together and to cooperate so that everybody can get an octet. This metal is willing to lose electrons. The nonmetal wants to gain electrons. Nitrogen's like, hey, can I have those electrons? And magnesium's like, sure, I'd like to get rid of these. So we take those 2 electrons away from magnesium. Magnesium looks like it's got nothing, but we understand that underneath there's this shiny octet of electrons. So magnesium is happy now. The nitrogen here now has a charge, right? Has a charge of 2 minus because it gained 2 electrons. Is the nitrogen happy? Does it have an octet? No, it doesn't. It needs another electron. Well, it can't get any more from this magnesium, but if there's 1 magnesium here, there's probably like a gazillion and 5 others, right? So let's bring in another nitrogen. Sorry, not another nitrogen, another magnesium. And this magnesium also is going to have 2 valence electrons. So nitrogen's going to bum an electron off of this magnesium. So now this nitrogen has a 3 minus charge. Is it happy? Yeah. Magnesium now has a plus 1 charge. Is this magnesium happy? No, it needs to get rid of 1 more electron. Well, who are you going to give it to? You're going to find another nitrogen atom. So enter another nitrogen atom with 5 valence electrons. So magnesium wants to get rid of one more, so it can give this to the nitrogen. Now this magnesium has lost all of its valence electrons, so this guy's happy. This nitrogen now has a -1 charge. Is it happy? No. This is where you might think, well, this is going to go on all day long. No, we're going to get there. Let's bring in another magnesium. It's got 2 valence electrons. So magnesium here wants to get rid of 2 valence electrons. This nitrogen needs 2 valence electrons. So they can help each other out. Now the nitrogen has 3- charge, magnesium has a 2+ charge. It took 2 nitrogens and 3 magnesiums so that we could get everybody to have an octet. So then the formula for the compound is 1, 2, 3 magnesiums, Mg3, and 2 nitrogens. That's the same result that we got from just looking at the charges and figuring out, well, how many do I need so that the charges add up to 0? But this is a better understanding of why that's happening. Any questions? So if we look at the formation of ionic compounds, the formation is usually quite exothermic. You make 1 mole of sodium chloride from sodium and chlorine, and it releases 411 kilojoules of energy. So where's this energy coming from? Well, what's happening here is the sodium is losing an electron, right? So that's an ionization energy. So the first ionization energy for sodium is 496 kilojoules per mole. We have to pay that to the nitrogen to get the electron off. And then we look at the electron affinity for chlorine. When chlorine gets the electron, it will pay us 349 kilojoules. If we add these up, though, we've only got 147, and it's actually in the wrong direction. So just looking at electron affinity and ionization energy, that would predict that this would be endothermic. It would absorb 147 when we know that it's exothermic and releases 411. So there's something missing, and lattice energy is the missing piece. Lattice energy is the energy associated with the formation of a crystalline lattice of alternating cations and anions. So I like this picture. So here we've got a whole bunch of sodium ions and chloride ions in the gas state, right? And they are attracted to each other. And so what this picture is trying to illustrate is those ions coming together, right? And just stick together because they're attracted to each other. The potential energy gets lowered when those opposite charges come together. If the potential energy is lowered, that means that energy has to go somewhere. Where does that go? It gets released as heat. So when we see the formation of ionic compounds being exothermic, it's not because the metal wants to lose an electron and the nonmetal wants to gain an electron. We talk about it that way, but that's not what it is. The vast amount of heat that's released is because when you make those ions and they come together, there's a tremendous lowering of energy, and that gets released as heat. They form a lattice. So we've got all these ions in the gas state, just, away from each other, and when they come together, they're just like, oh, this is good. Lower in energy, and so we get heat being emitted, and that's the lattice energy. To calculate what the lattice energy is, we use what's called a Born-Haber cycle, a hypothetical series of steps that represents the formation of an ionic compound from its elements. And really what we're doing here is using Hess's law. So here is a Born-Haber cycle for making sodium chloride. We're starting right here with the element sodium and the element chlorine. And we're going to imagine a series of steps and add up the energy changes. So we need to get sodium from being a solid into it being a gas, and that's going to require us to put energy in. Then we're going to take this half mole of chlorine molecules and separate those into their atoms, and that's going to require energy. And then we're going to make these sodium atoms into ions. First ionization energy, we've got to put more energy in. The chlorines need to become anions, and that's exothermic, so the energy is going to come back down a little bit when we got chloride ions and sodium ions. So if this was all that was happening, then the energy change would be this, and it would be endothermic. You'd be absorbing energy. But when you've got these separated ions, now they're going to be attracted to each other, and they're going to go, whoom. It's literally that noise. Whoom, right? So they all just, whoom together, and that releases a whole bunch of energy. This is not something that's easy to just measure, right? Well, how do we figure out what that is? Well, we can find all of these other steps. We can measure the enthalpy change when sodium chloride is formed. So we know it releases this much energy. We know how much energy it took to vaporize the sodium, to break the chlorine into atoms, to ionize the sodium, how much was released when we ionized the chloride. And then the difference is the lattice energy. Yeah?
How do you have 1/2 as a...
That's a good question. So if we're talking about atoms and molecules, 1/2 of a molecule makes no sense, right?
Half a mole?
Half a mole.
Okay.
So this is 1 mole of sodium and half a mole. So you take half a mole of chlorine atoms, molecules, and break them up, and now you have a mole of chlorine atoms.
So if you had 1 molecule of sodium, you would have no molecules, or like you wouldn't be able to, you'd have to have 2 in order to...
Yeah, if you were looking at it on at individual molecules and atoms, you'd need 2 atoms of sodium and 1 molecule of chlorine. Yeah.
Okay. And how come it's not 2, how come it's not just 2 Na and 1 Cl2?
Another good question. You're full of them.
Sorry.
No, don't be sorry. I love it. So yeah, so why isn't it balanced 2 sodium and 1 chlorine? Because we're looking at how much energy is released for 1 mole of sodium chloride.
Oh, okay.
And so this is like those heats of formation that we talked about, the formation reactions, where we're looking at starting with elements in their standard states and producing this compound, 1 mole of it, and then we have to balance it, but we can't have anything but a 1 on the product. So that's where we end up with the fractions.
You just change it so that way
Yeah.
it'll be a 1. Okay.
Yeah. Yep. Any other questions? Lattice energy is affected by ion size and by ion charges. So if we look at the alkali metal chlorides, lithium, sodium, potassium, cesium, we find that cesium releases less energy than lithium does when it forms a compound with chlorine. So why is that? Lattice energy depends on how close the ions are in the lattice. So remember we mentioned Coulomb's law before, and here's just a little piece of Coulomb's law. The energy is proportional to 1 over the distance between them. So this is when we were talking about the magnet on the fridge and how many pieces of paper are in between, right? The more pieces of paper between the magnet and the fridge, the less it sticks, right? And eventually it won't stick at all. So lithium and chloride can get closer together because lithium is small. Cesium and chloride cannot get as close because cesium is a bigger ion. And so the distance between them is larger, which makes the energy smaller. So these guys can get really nice and close to each other. They release a lot of energy. These guys cannot get as close. They release less energy. Ion charge has an even bigger effect. Here, looking at sodium fluoride and calcium oxide, we've got minus 910 kilojoules per mole versus minus 3,414. The sizes here are very similar. The distance between the nuclei, 231, 239, almost the same. But the difference is, here we have +1 and -1 charges. Here we have +2 and -2. So this is like the stronger magnet. It's going to hold on better than the weaker magnet. Coulomb's law says the energy is proportional to the charge on one times the charge on the other. So for sodium and fluoride, we've got +1 times -1, which equals -1. For calcium oxide, we have +2 times -2, which equals -4. So based on charge alone, this would be about 4 times as much energy as this one. And here, 3,400, roughly 4 times 900. So higher charges, larger lattice energy. Smaller ions, larger. Lattice energies become less exothermic with increasing ionic radius and more exothermic with increasing magnitude of ionic charge. So this is a kind of question that could show up on an exam. There would only be one. Arrange the following in order of increasing magnitude of lattice energy. Lithium bromide, potassium iodide, and calcium oxide. So we're looking for 2 different factors. We're looking for the charges and the size. Because if the charges are bigger, the lattice energy is going to be larger. So let's look at what these ions are. We've got lithium, which is a +1. It's not iodide, it's bromide. Bromine -1. Potassium +1, iodine -1. Calcium +2, oxide -2. So the charge has the most effect. So which of these has the largest charges? Is it calcium oxide? You guys awake? Look awake. So this would be 2 times -2 or -4, and these would both be -1. So this is like 4 times bigger just based on charge. We're supposed to arrange these in order of increasing magnitude of lattice energy. So we want the biggest one last. So this is going to be the biggest one because charge is the most important. So that's going to be the biggest one. And then we have to look at the other 2 and see, well, how do they go? Well, we have lithium and bromide, and we have potassium and iodide. Which has bigger ions? Which is bigger, lithium or potassium? Potassium's bigger, right? And here, bromine or iodine, which one's bigger? Iodine's bigger. So the blue ones here, bigger ions. They cannot get as close to each other. These are smaller, they can get closer. So I kind of think of these guys as like like two people wearing those, T-Rex blow-up suits, right? I mean, this big puffy thing, and you're like, I can't get close to you, right? And these guys are like wearing some regular Halloween costume, and so they can get up and snuggle up and be real close to each other. So this is going to have a higher ionization energy because they're smaller, they can get closer. So lithium bromide will go in here, and potassium iodide will go over there. We are almost done. Hang in there. So, does the bonding model explain our observations of properties of ionic compounds? Thankfully, yes, it does. We observe that ionic compounds have high melting points, and we can explain this because they have non-directional bonds. So in this solid, we have attraction between positive and negative ions on the right, on the left, on the top, the bottom, the forward, and the back, right? So it's attracted in all different directions, and so that's going to hold it together very tightly. It's going to have a high melting point. Ionic solids are non-conductive. They don't conduct electricity. Well, in order for electricity to flow, you have to have charged particles that can move. So here in the solid, they can't move. They're fixed in place. But if we dissolve them in water, now we have individual ions, charged particles that can move, and this will conduct electricity. You can also get conductivity if you melt it and make liquid sodium chloride, which is not very easy to do.